Okay, shall we start? Okay, please sit down. Okay, I need another minute. Test, yeah. It's working. Sorry for that. Okay, so let's start. Thanks a lot for coming and facing the horrible Bangalore evening traffic. So you're all here, and we have another 100 to 200 participants on a web live stream. So yeah, I want to tell you something about IBM Watson IoT and our cloud. And then we have some interesting presentations and live demos about a tool which is called Node-RED, which is a graphical data flow editor. And this is an open source tool. And you can do amazing things with that. Then we have a little demo on a Raspberry Pi, how to connect that to the IBM Watson IoT platform. Then we will do some introduction to ApacheSpark, how we can use ApacheSpark for IoT data analysis, and then we will finish with a demonstration of cognitive deep learning based algorithm to detect anomalies on IoT sensor streams. Okay? So this is the new IBM headquarter for IBM Watson IoT, which is based in Munich. This is around 500 kilometers from where I live. I live in the bottom left corner in Switzerland. I'm half Indian and half German, and sometimes IBM pays for me to visit my family and to give some talks in India. So why is IBM doing IoT now? Why is everybody doing IoT now? So the reason is we have 15 billion connected IoT devices at the moment. In a couple of years we will have 40 billion, and if you contrast that to the world's population, so let me sit down that everybody can see it. If you contrast that to the world's population, you see there are many devices per person on the planet. So the central protocol which IBM has chosen to do IoT is MQTT, which is a protocol which IBM invented and which Oasis picked up as an open standard. And nearly every IoT cloud provider now is using MQTT for connecting IoT devices. And not only the cloud providers, also the gateway providers, they are using MQTT. So if you are doing IoT and you are hacking on the Raspberry Pi, then you are doing something wrong, because the basic idea is you get these devices finished and you just choose your cloud and your internet credentials, and they will automatically hook up to the cloud and you can remote control them. That's the way how it works in future. There is already one device which supports this with the IBM cloud, which is coming from Cisco. So you can push analytics defined and configured in the cloud to the device without even touching the device, and you can do remote updates and all over a secure channel. So that's basically the whole picture. So you have the device. One of that devices is here. It's a Raspberry Pi, There are more than 250 which we are supporting, and if we don't support it, you can support it yourself because it's an open standard to talk to the IBM Cloud. It's MQTT. Or HTTP. In case you're behind the firewall, then you can also tunnel the data through HTTP. The IBM Watson IoT platform is a MQTT message broker. So it's all based on publish and subscribe paradigms. We have REST APIs for device management and also for getting data in and out. And then we have the analytics part, which we will cover mostly today. So this is a Raspberry Pi with a so-called SenSet attached. This package is around $50. It has some outputs, but it has a lot of sensors like accelerometers, temperature, humidity, sound, proximity, ultrasound, proximity sensors. And in order to hook this up to the cloud, you need 6 lines of code for initialization and another 3 lines of code to send a temperature value via MQTT with quality of service level 2, which means it's guaranteed exactly once delivery. That means we take care of everything. We take care about load balancing, failover. So we are running this system on more than 50 data centers worldwide, and if something fails, we take care about recovery. So as you can see here, you are not configuring any endpoints like IP addresses or ports, so that's all handled by the library. But you could, if you want to do, you can access the MQTT layer at the bottom as well. Actually, we can try a little demo later, where you can use your smartphone with a little browser application running JavaScript. One part is accessing the accelerometer sensors, and the other one is sending the data via MQTT with the MQTT JavaScript library to the cloud. And it's a fun game because you can shake the device and I can calculate the energy you create, and then we can see who the winner is. So if you have time, we can do that later. If you want to know how to do it, what I've told you until now, there is a free Coursera course on it, and IBM is proud to host the first non-academic course on Coursera. And we are currently launching the second one. It's on data analytics, and it will be live in a couple of weeks. Yeah, those are the 3 other courses. We are preparing a specialization. One is on exploratory data analysis, so how to plot and how to calculate statistical moments. The other one is concentrating on time series analytics, and the third one is on AI methods, so basically mostly deep learning. But that one will be available next spring, the last one, so we are producing it in sequence. So I've told you everything about the central nervous system of IoT, and after the other presentations I will tell you something about the brain of IoT. But now I would like to hand over to the Node-RED presentation. Okay. Has to be kept here upside down because that's for the live stream, and that's yours.
Am I audible? Thanks, Romeo, for the excellent introduction. Hi, I'm Amit. I am a part of the Watson. I'm part of the IoT tooling team, along with my colleagues Jeffrey and Hari. We will be talking about Node-RED. So after this, I won't bore you much. Just 15 minutes. Give me just 15 minutes to explain something about the Node-RED. Then we will have a short demo about 10-15 minutes, and then I will hand over the baton back to Romeo. So before I start, is there anybody who is not aware of Node-RED? Okay, quite a few. Thanks. Otherwise, generally the issue that happens is people know more about Node-RED than myself. So you are going to spare me that agony. Thank you. Let me start with what is Node-RED and how it came to picture. So this is a tool which was developed by IBM. It's a complete drag and drop tool. It's open source. It's made available on the GitHub, and it's also available on the Bluemix. So the idea with Node-RED is develop everything using just the widgets. We have the widgets available. Just drag and drop the widgets, and you can have your flow running. I dare to say that initially the target was probably no coding at all. But if I say that, I'm going to receive a lot of big bets. Of course, there's some coding, but it's at a very bare minimum. This was developed by, as I said, it's developed by IBM, but we have completely open sourced it. It was developed by Nick O'Leary and Dave Conway-Jones. We have made it available. We have open sourced the source. You can check on the GitHub. You can also contribute towards it. We keep looking through the nodes. Initially, this project started with something like probably just 10 or 15 nodes, but there are now more than 600 nodes, and we keep on adding further nodes over here. So this is, as you can see, this is user-friendly, completely browser-based development. You just need the browser, and you can make use of Bluemix for the development, or you can have the Node-RED running on your system also. It's written in the underlying development platform is Node.js. It's Node.js. So all the capabilities of Node.js are there available. It's lightweight and it's event-driven, non-blocking. Also, social development. You can connect it to the Twitter. And the entire flow itself is stored in the form of JSON format. So it's very easy to port it across. You have one Node instance running. If you have all those nodes available in another instance, you can just copy the flow as it is. This is something which I already told. IBM developed it, but it's open source. And look at the figures: 325,000 installs. And this is growing every day. More than 600 nodes. Initially started by IBM, but now there are more than 50 non-IBM members contributing towards it. And apart from IBM, there are other companies, Sense Technique, AT&T, Red Hat. The last thing is very interesting. Now it's being made available as a part of the Raspberry Pi. So if you are using the Raspbian module, the Raspbian OS on Raspberry Pi, comes as a part of the instruction itself. This is just a very small snapshot of all the different nodes which are available. You can see the input node here got inject, output is all these different nodes. MQTT for connecting to MQTT, HTTP nodes, then WebSocket. For output we have the debug. You can just connect these two for a very simple Node-RED application. So it doesn't take more than even 10 seconds to develop 3 points. Then we have the function nodes where you can write your own functions. Switch mode, HTTP request. As far as the social nodes are concerned, you have got email, then Twitter. You can store on the MongoDB HDFS. They are available as a part of the Bluemix offering. If you have connected to the Bluemix service, if you have added the Bluemix service, you can make use of these nodes and send your data to this particular storage. Finally, we have the Watson nodes for natural language classification, then speech to text, text to speech. Now this is about the nodes. Let me just show you a small live demo of Node-RED. So this is the actual Node-RED installation. Let me show us very small demo. Probably this is the smallest Node-RED flow you can see. That's it. This is my, in just these two, just adding these two nodes, I was able to get a flow running. All I did was add a debug node, add an inject node. And I'm going to push, I'm going to set a timestamp from this to over here. Now this is all running on the server. As you can see, this is not a local host. It's completely running on the Bluemix. But you can have the same application running on your local instance also. If you install Node-RED on your local system, you can do the same over there. Now, what I showed you was the existing Node-RED as is. However, we are adding lots of more functionalities over there. So this is what we call IoT tooling, and that's Node-RED on steroids. So provide you with a more closer integration to Watson IoT. You can do a simulation, which is one of the main things in IoT. Many of the cases, you'll be having lots of devices. You have probably some hundreds or thousands of devices. And instead of actually purchasing this device or going for the device, you would actually first want to do a simulation. Get all the devices, let's see how the devices work. So that's the consideration. And that's one of the additions which we are doing in the IoT. And finally, some rudimentary UI functionality. Not a major, but at least you should have some sort of forms wherein you can look at we can have text boxes, we can have radio buttons, those kind of stuff. So this is something that we have added as a part of the IoT tooling. And finally, we are addressing the scalability and the version control. So these are something that we are adding now as a part of the tooling capability. Now these are some more tools which we have added. Some more nodes which we have added. How many of you are aware of Watson IoT platform? Okay, let me just give a very brief introduction of what Watson IoT platform is. It's IBM's cloud offering for Internet of Things, and in which you can do device management, device monitoring. You can see how much is the data flow going in, and you can set accessibility. You can create your own cards on the platform. So all is available as a part of the platform offering. Now we can also create devices and the device types. That's where these nodes come into the picture. The device type, device manager nodes. In fact, this is a demo which Jeffrey will be showing as a part of how we can easily create the device types, device instances. And as I told you, as a part of IoT, we need to provide you with simulation tools. So these are the different nodes which are provided for simulation capabilities. And let me go back to the browser to show this. This is okay. Now this is a platform which I was talking about. What's an IoT platform? As you can see, we have lots of capabilities over here. We can see we can register multiple devices. Let me just register a device. Sorry, I know this is a part of your demo. Let me just add it. Yeah, sorry for the initial hiccup. The session had timed out. So we can see various devices over here. Let me just create a device on the fly. That's it. I created a device on the fly using just the platform capabilities. And you can see this is the device which I just created. The device type is 0123. I could have given any name over there. And and the instance is 1, 2, 3, 4, 5, 6, which I just created. Now this is a very basic introduction to what's an IoT platform. Now let me go back to the tooling part. So the devices which I created manually, those can also be done using these tools, these nodes which I am showing over here. Next, you can do the simulation, and finally you can have a very basic forms. We can also control the existing nodes. We can enable or disable the nodes which are present, or uninstall them. And they are part of the JS Foundation now, JavaScript Foundation. So that's it. I would like to. So the actual live action will be shown by Hari now.
Shall I unplug? This is mine.
This is yours.
Thank you.
Hello, am I audible? So as Amit said, so we are developing additional features to Node-RED so that creating an IoT solution will be more easy. So this is this is a sample that we have created using IoT tool. So this is available in GitHub. Just just search for IoT climate control sample. You will end up in this GitHub page. So let me see. I'm hiding for a few people. Yeah. So once you can see this deploy to Bluemix button. So once if you click on the deploy to Bluemix button, so it will take you to this page. So here all you need to do is log into your Bluemix, and then it will show you this page. So where you can give your application name. So whatever name you want to give, like this should be a unique name. That's what it needs. Like for the URL purpose, it should be a unique name. And then you need to select your organization and space that where it will deploy in your Bluemix, and then press on this deploy button. So for the time, it will take around 10 minutes to deploy. So for the time sake, I have already deployed this. So I have deployed this EGL demo EGLA with that option. So here you can go and visit the application. So that will be deployed with this. So this is the chiller example that we are developed with the Node-RED. So there are a lot of description about it. You can go on and read like what this application does. It's basically has one simulator that will simulate an virtual temperature gateway, and thermostat gateway, and it will send a temperature data to the platform. So all this flows, it's just an example flow. So you can deploy it, and then you can modify it as per you want. So that's what I'm going to show you. So we have this, all description about what are the steps to do to go to the platform, and what everything will be available over here. So let's directly go into the flow. So as Amit said, the about simulation, no description, and what are the features that we have added or shown here. So you can directly go to the demo right now. So this is the entire flow for the this sample application. So this is a chiller application. So as Amit said, so we have an simulator option. So what if person don't have a device? So they don't, before purchasing to a device, I know what are the data that I can get from a device. Like, for example, if you want to control a room, so what will you need? You need a temperature or humidity, environmental parameters that you may need to obtain from a device. Or for example, let's take a car. So if you want to do a car, means you may need the GPS location and other parameters like your drum speed, other things. So based on your solution, you know that what are the parameters that you will acquire for the solution, like from the device. So we have this simulator option. So I'm just running the simulator right now. So via this simulator, let me first go to the platform and show you so what I have in the platform. So yeah, this is my platform. Nothing is here. There is no device types. There is no device currently available. So, but here we have this simulation page. So here we can create multiple instances of. In this case it's a thermostat. So I am creating 3 instances of thermostat on the fly here. So once I click on the create button, I think it's loading. So it will create 3 instance. It will show 3 instances of the device running. Let me refresh once. So I think something is slow. So it will create 3 instances. You can see the values that are simulated over that simulated in that place, and so this is the flow that actual determines the behavior of the simulator. So when we go here down here, so here is where we determine the behavior of this device. So we have a thermostat, data structure, as I said. So what kind of data that you may need from this device. So this is available. Here you can go ahead and add let's add another type of data like humidity. So let's say we will add an humidity, and we will set the data type as number and you say 20. And here we define the behavior of the simulator. So I am just going to add this thing. So what I am doing is the humidity value will simulate in a way that it will rise up to 26 and then fall down to 20. So this is the basic logic behind it. I'm just putting it over here, done, and then deploy. So once it's got deployed, you can find you can see the humidity over here. So let me create once again. This should come. Yeah. So as you see, this is before deployment, before making the changes. So let me make the changes over here. So we need to add the one more parameter, humidity. And I am defining the behavior over here. I have added the behavior for the humidity and then just deploying. Yeah, it's got deployed. So if you go here and if you create a device, so okay, so now you can see humidity also comes here, and it is I think I have given it as strings. It adds as a string now. I need to give it as a number. Yeah, so you can see the humidity is now rising from 22, it will go up to 26 and then fall down to 20. So this is, we can add more, think the humidity is a sensor. So we can, there is no device currently with me, but I am able to simulate the data, and I can view it as well. So if you go, there is view dashboard here. So if you click on that, actually we are plotting the humidity, plotting the room temperature, and we are plotting it in as a graph. So this is the actual simulated data that is going to platform and coming back, and we are listening it to the events, and then we are plotting it over here. We can see that in the flow. So this is the monitoring flow. So let me reduce some resolution. So basically we also have this alert mechanism over here. So basically we can give the threshold temperature. Currently we have given highest threshold temperature is 36 degrees Celsius. So if I go to the simulator and I edit the actual temperature more than, say I am giving it as 50, so that is more than the threshold temperature. So if you go to the dashboard, you will get the alerts saying that check out the temperature is more than the critical what you have set, and as you see, the entire application, the entire thing is done with Node-RED, and these flows are available in GitHub, and anybody can deploy it and use it. So you can, so this is the where I said, so we are getting the this is where we are actually acquiring the configuration from the alert tab, and this is where the alerts are sent to the as I said, so we are listening to the platform, and we are plotting in the graphs and dials. So and this is the simulator flow where so this is the entire simulator flow. The start simulation and stop simulation are there to start the device, start and stop the simulation, and basically you can see here start or stop that option. So once you start, the simulator will start the flow, and based on your behavior you describe for the device, it will send the data to the platform. And yeah, this is the entire simulator dashboard logic. You can just leave it. Yeah. That's all from my side. Yeah.
So is it going back to the vaccine platform?
Yeah, actually, yeah. Let me show you. Okay.
But to answer your question, I guess it does actually go back and
Yeah.
create the actual device on the platform. We usually start the other way around. Yeah, so that's what this particular tool helps you to do, right? So how you actually, so whatever you had to simulate, it will actually go back and it does wire back and actually go into the platform.
And also,
Those two
yeah, I'm just
able to see that.
second. Okay. I will just show you one. Give me a minute. So here you can see the devices that I have created using the simulator, and we can. Yeah, correct. This is choice plus. This is off. Yeah. You can also do bulk registrations. You can also get all the device you have registered in the platform, and you can also, delete a device, and you can do all sort of operation using the device type node and device management node. And the device type node will help you to create the device types. Before if you want to register a new device, the device needs to mention a device type. So how to do that? This is totally programmatical way. So with this you can with the device type node you can create a device type, and then you can use the device management, the device manager node to create a device in the platform and on the go. Everything is based on, like, for example, if you have a solution where a user scans an QR code, and once they scan it, you make an you make an HTTP request to the flow, and based on the details you scan, you can register a device on the fly instead of going to the platform, and you don't want to expose the end user to the platform. You can you just get some data, or even predeterminedly you can keep a data for them, and you can use those details to the those two nodes to access the all device and device type functionalities available in the platform.
Just one more. For example, you have a very large energy or utility plant, and there are thousands of sensors that are streaming the data in real time. So like, I mean, if you actually want to say differentiate between, say there are multiple zones, and if you want to figure out from which zone the data is coming in, so is there any option in Node-RED where I can actually go and say, okay, zone A is having 50 sensors, and this should be the temperature threshold for this zone, and okay, you go to zone B, that's a different set of sensors that works like that. So can you do that easily over on the Node-RED? Yeah.
Yeah, basically you want to group your devices and apply some set of logic based on the device grouping. So the device grouping, and you can keep one device type, like zone 1 is one device type, and you put all the devices, most of them will have same behavior, right? So you can put all the thing in one device type, and you can set rules in your logic in the Node-RED based on if this event is coming from this device type, and this is the device ID. So if this device type, this is its device type, then you do this kind of operations. So those can be done. So let me show you. So here in Node-RED, so we have this application node. So here we have the device type, and device type, even though you can even specify a particular event sent by all the devices. Like for example, you just want to monitor the say what is temperature or in a particular zone. So that device type, just listen to that event, and based on that you can put your logic after this. Yeah, basically, it is hierarchical. We can create the hierarchy based using device types. So, anything else?
My question is regarding these notes about device management. So it's already released in open source project, or it's still with you for
So it's already available on the GitHub. Now, on the Bluemix, if you want it, you can deploy the application from GitHub over there. If you want individual nodes, those will be put on the LPM-based finish shortly, maybe in a couple of days. Now, if I want to store this data somewhere in the back end, and I want to do some predictive analytics on top of it, so I need to put it on back into Bluemix platform somewhere with Automation Cloud in or I can do it in my own in-house storage.
So actually we are in this sample itself. We are putting the alerts information into the cloud and database. So you can integrate with your own database using REST APIs if you want, or you can use the cloud as a database for the purpose.
next regarding scalability. So let's say I'm having big system where thousands of sensors are getting data continuously. So let's say I'm storing data in the cloud and then processing it. So we have scalability option there. We can spin up multiple cloud instances based on traffic and all that. Do you have anything for Node-RED?
So if you look at the latest IoT app node, there is an option of checking the scalability, wherein you can distribute the same flow across multiple instances. I don't know whether it's installed on this particular system. If you look at this option, scalable, you can actually set the scalability over there. So you can then distribute to multiple instances.
You can also use the auto scaling mechanism of Bluemix to automatically scale up and scale down its node.
Can you speak louder, right?
Apart from climate control use case, build the user use cases for IoT?
Oh, this is just, this is the first release of us. So currently has only this as a sample, but it is very easy. You can modify this sample as per your needs. So we have simulator that helps you to, that is generalized to do multiple device simulation, and we have like basic workflow is available over here. So you can add your own, you can modify this flow as per your needs. So to get your end solution, and we are also planning to put out more samples over here. It will be available soon.
So, if you're saying the product itself, can you be installed in the local ecosystem also?
What is leveraging on the,
What's the additional advantages that we get? So if you get I believe this will take up again, but there are quite a few services which are available on the business. So all these capabilities, if you want, integration is very straightforward. Like for example, if you want to like use or
Okay. So maybe we now hand over to Hasana, and one thing after this demo we will have some tea, coffee, and snacks, and I hope you still are staying for my talk after this.
Just share it across.
Understanding or introduction on Node. So I am just extending their part to add how we can configure Raspberry Pi chip using Node and get the ultrasonic sensor value or data values from that. So already
So
already Amit and Hari have given information and overall introduction on Node-RED. So here we will just verify how we can add Raspberry Pi nodes on the Node-RED. So I have there is terminal on Raspberry Pi, and in this you have to give command node/red and node library node flow will get start. Node flow will get start, and you will get this web-based interface for the Node-RED. So here I have already mounted ultrasonic sensor on the breadboard. So and it is connected with the Raspberry Pi chip. So its VCC is connected to VCC. Ground is ultrasonic sensor has 4 chips, 4 pins: VCC, ground, echo, and trigger. So VCC is connected to VCC of Raspberry Pi. Then ground is connected to ground of Raspberry Pi, and echo and trigger. These two pins are connected to GPIO 7 and 11. Okay. So Node-RED has already library to support this Raspberry Pi pins. We have installed this already on this chip. So I will directly go to this library. So as Amit and Hari covered, there are lot many nodes are there: input nodes, output nodes, different type of function nodes. So this is these are the nodes available from the Raspberry Pi chip. So this is the RPI SRF node. It is specially configured for ultrasonic sensor. So if you have to just drag this node, drop in the flow, and double click on this node, you will get pin information. It will show you which pins to program. So here we have, as I already told you, we have connected echo and trigger pin to 7 and 11. So we will give pin numbers as 7 and 11. We will give some name to it: distance, sense, done. So our node is done. Node is added in the flow. So we have to check output whether it is giving value or not. So go to output node, and here debug node is there. Just drag and drop this debug node. Now connect these two nodes and say deploy. Okay, now it is giving values here. So 6 and 7, 0, you are getting values from the sensor. Now we will do some programming to check on this device, on this Raspberry Pi only, to check whether we have to suppose do some measurement, whether that obstacle is at what distance, and to take some decision. So for that we have some function nodes here. We will write a small function. So we will give name as text distance. So we will now set one. We will test which LEDs to glow. Means if suppose distance, if obstacle is less than 50 centimeter, then we will glow one LED. Otherwise, we will glow another LED. So for that, we will say we have to send 1 and 0 to these LEDs. So we will define two variables. So we will give payload 1. Then variable of. We will define payload 0. After that, we have to we have to write the logic to measure the distance. So we are getting now distance value in the message payload. So if message dot payload is less than 50, return on, comma, off, else if message dot payload is greater than or equal to 50, return off, comma, on, else return off, comma. And we have two LEDs here, so this function will require two outputs. So we will just increase output here to 2 and just say done. And we have to now connect output of distances to input of this check distance. So this check distance will get input value. Now we have to program. We know that there are two LEDs here, and these LEDs are connected to pin number 29 and pin number 31 on the Raspberry Pi. So we have to get output. We have to send output back to LEDs. So we will select here GPIO pin number. You will get all the GPIO pins mapped for this Raspberry Pi in this node RED. So pin number 29. So it is digital output. So we will set it to initialize it to low, and we will give it name near and say done. Same way, we will take another GPIO output pin. It is pin number 31. Initialize pin state to low and set to far. So just drag this to nodes. Okay, and now send deploy. So it has an obstacle more than 50 centimeters. So you can see that far LED is 1, and if I put my hand here, near will become 1. Otherwise, again far will become 0. So in this way, you can easily program any hardware. There are support for a lot of hardware chips on this Raspberry, like Raspberry Pi on node RED. So you can deploy any library in this node RED and do the programming easily. So it is just a 10 minutes time. So in that you can do some minimum, basic minimum logic. Okay. So yeah. So
Done? Questions?
yes. So any other questions?
Okay, I suggest a 10 minutes break. You can grab your stuff and come back again, and then we can do shake your smartphone game for 5 minutes, and then let's go a bit deeper into the neural network and ApacheSpark stuff. Okay? Good.
Okay, thanks everyone.
Thank you.
Thanks.
I have a question. So here the Node-RED module that we run in the Raspberry Pi module, that is basically injecting data via MQTT into the backend, or how is it? Is it through MQTT, or how is it sending the data?
This one is it?
Yeah, here in this
Okay,
case.
if I take the question out. So currently it's just using Compo. I believe.
Yes,
It's a code there.
No, but then we are running Node-RED module in the Raspberry Pi.
True.
So
So MQTT will be required if you want to communicate with the platform, the cloud platform. Over here it's not needed.
okay.
If you can check the, if you look at that flow, it's more of just Raspberry Pi, function node, and the
So it's
debug node.
this app is directly communicating with the Node.js
Yes.
thing
It's
actually.
already communicating with the Raspberry Pi over the COM ports.
Over the COM ports, okay.
So that's why when
this
it
is
clicks over
using
there,
COM protocol.
Yeah. So
Right,
if you
right.
that's why when you click over there, it should give you an option.
Okay.
These ports over there.
Okay, okay.
This
So,
kind of
so,
device.
so the Raspberry Pi device that is listed here is over COM port.
If you have the
So you can do rule-based programming and all here.
you can actually, yes.
You can all those things.
बंद करू का? बंद करू का? Should I close this room now?
Yeah, you can close it. So you can take coffee and relax.
Okay.
Me not, I have to.
Yeah, yeah.
I just pull this, okay?
So actually, you are stressed out now. You have just come from the flight and started doing.
Yeah, I was done yesterday evening. It takes 24 hours. Yeah, I was in Oman
Oh my god.
and eating dates in Oman,
Okay.
Muscat.
Actually, I have done complete demo to send data to Watson IoT, but
Yeah, no problem, no problem. I knew that, and I even liked that you managed to use your phone. But if it's not working, there's no chance. That's the only drawback if you're doing this at IBM locations. There are two drawbacks. One is the network. The other one is that you have to register each and everybody to get the entrance badges. It's also a pain.
we have actually came earlier
Okay.
to set up all that things. But they told us that the cafeteria will be available after 6 p.m.
Okay.
Don't have any other choice to
IT guys were already left, so we couldn't be able to contact with them.
Yeah, but I knew it's not possible within 1 hour to set this up. No chance.
Anirudh, so I just wanted to pick your brain and say how to start with contributing to some open source analytics or project or some
Okay, so-
academic research. research
What
project.
is your interest?
So basically just wanted to explore, say, deep learning part of things
Okay.
and its application in analytics. So I've been started reading some papers and then
Okay.
So
It depends a bit. If you are fond of Spark, then you can go for Deep Learning for J.
okay.
If you want to get the basics, there's a free book on deeplearningbook.org which you can read. And there are some good introductory tutorials on TensorFlow, but then they stop at a certain point. But in my opinion, the tutorials which are included in Deep Learning for J are far better. And today I will show Piano and Lasagna.
So how do you learn by yourself? So that is something.
I was actually just listening to the talks on YouTube of Adam Gibson, which is the founder of DeepMind. Oh, thank you very much. Did you get something? Okay. And Vinit, Prasanna, did you get something to eat? There's left. Okay. Yeah.
If you want to grab something, you can.
No worries. I'll eat while you are shaking the device. So actually they, what about, so this guy is giving really good talks on YouTube.
DeepMind is Google's.
No, SkyMind, not DeepMind. SkyMind.
But just keep also.
Yeah, exactly. And this Adam Gibson has many good tutorials on YouTube, and he's also in Chitta 24/7. So if you have a
Yeah, so obviously there is a theory part of things and you can learn it by YouTube videos, reading. So how do you apply what you learn?
Do it yourself. Just pick any data set and try to implement a classifier using deep learning. So I will show an anomaly detector today. You can grab this. I'll open source that, so you can start with that. And the examples, there are public data sets, and the examples they are including the public data sets. So that's a good starting point. So the main thing you have to learn always is to design your neural network accordingly that the error decreases. And if you start it first, it just oscillates. So that's the main problem. Yeah. Welcome. So I'm just preparing the game. Give me 2 minutes more. So this game includes the IoT dashboard. And by the way, IBM has a free tier, so I think we didn't tell you that. So if you go to this URL, you get a free trial for 30 days, and after that you are ending up in the free tier. And in the free tier, for example, the Watson IoT service has 20 devices for free, so you can basically do anything what you want to do at home. And that holds for every service in Bluemix. So you get 1 GB of storage in NoSQL and I think 1 GB in a relational database, and I think 5 to 10 GB on ApacheSpark with I think 2 or 4 cores. So it's quite nice. So anything from, let's say, small scale private stuff you can do completely for free on the same SLAs like we have for our paying clients. Just a side note. So this is basically the Watson IoT platform dashboard, and what I always have to do, because I'm very unstructured and not well prepared, I have to delete all the devices from my last demo. You can imagine that I'm running this demo a lot of times. So now we can start from scratch. And I also have a Node-RED instance running, capturing data from your smartphones. And this smartphone data I will process, but very easily I will just transform the hierarchical JSON data into a relational one, and that's basically it, and store it to a relational database. In case I find the flow, yes, here it is. So that's about the flow. It's not doing anything because nobody is sending data. So now you have to help me. So you need a smartphone and you need internet connection. I don't know whether we have, or whether you have, but let's give a try. So it's a similar URL, it's ibm.biz, but then let's just duplicate this. It's boom, boom, shake, shake. So first come, first serve. If you open this URL on your smartphone, you will see this application, and you have to enter a unique ID, and that one you have to remember because we give you a second dinner if you are the winner. So just put 8 small characters and then click OK, and the second thing is the password. You don't have to remember it, but you have to put only small characters, no numbers, no capital characters. It's ibm.biz/boom boom shake shake. So you shake shake, I do boom boom. Okay, what I will do is I will not occupy one of that 20 device spots. I will just see whether you are lazy or not, and whether I see data coming in or not. In 20% of the cases it doesn't work, I don't know why. So hopefully today we are not in that. URL again? Okay. Boom, boom, shake, shake. Anybody able to open the URL? Okay. Are you sending data? Okay. Is it counting? Okay. But it's counting messages also? Okay, so then I should definitely see data now. Yeah, it's coming. So it's the accelerometer values. Yeah. So it's working. So you are sending data to the IBM Watson IoT platform using MQTT via the MQTT message broker. One thing I have to do before we can start is to empty the relational table. Because of course from the last game there's still some data there and you don't want to compete against the previous participants. And the difference from today to all the previous demos is that now I have a webcam filming you. And that's something I always really miss because it's really fun if you're sitting here watching the people shake the device. So if you don't want to be filmed, just tell me, just raise your hand that I know. Okay, you're not shy, huh? Indians are not shy. So I just will open the DashDB. That's by the way IBM DB2 version 10.5 with 3 important features. It has a column store, so it's not a row store. It uses the SMID instructions on the CPU, and it has a fast compression, so it's a data warehouse appliance. And there you have also, I think, 1 or 10 GB for free. But you could use any other relational or non-relational database. So we have MySQL, MongoDB, and Postgres, CouchDB, and of course, as we see later, ApacheSpark there. I haven't ported the demo to ApacheSpark, by the way. It would run out of the box with the same SQL statement using ApacheSpark SQL as well. So for those who want to stay beyond 10 p.m., we can port the demo to ApacheSpark later. So let's just get rid of all the previous I think I won't use this anymore, otherwise this guy is already hating me. You can keep it. I think I will destroy it otherwise. Okay, I just use a normal microphone. Thank you. And I can sing boom boom while you shake. Okay, so the table is called, let's see how the table is called, because to store this data in a relation database using Node-RED, all open source, you need exactly 1 parameter, table name, nothing else. All the rest is done via Cloud Foundry, and that's maybe one advantage if you run this in Cloud Foundry and Bluemix. You don't have to care about any configuration parameters anymore. All the credentials are injected. And they have included a very, very cool feature, which is online syntax checker, which completely messes up my JavaScript engine from the browser. Therefore, I will type it here. And as you can see, I lost my second hand, so I'm really slow now. So let's delete all data from the previous demos. Seems to be a lot of data. And once this statement finishes, we have an empty table. Then what we can do is we can connect basically this line here and publish. And what this does is, as I told you, it will flatten down the schema, because it's a hierarchical schema, JSON objects, and we flatten this down to a relational schema which fits the database, and that's basically the 4 column names of the table. Okay, so let's see whether that statement ran. Yeah. just die. Delete what? We have a hanging SQL command. That's never happened before. What to do? Okay, I want to cancel the current comment. So how do I do that? Good question. Doesn't tell me. Yeah, sometimes the UI is a bit small because of the projector, but I don't see any option to cancel that comment. So you know what? Let's take this to the later stage once this weird comment finishes. Let's start with ApacheSpark. Keep your device like it is, and we can play it later, okay? So another risky thing I'm doing. So, okay. Oh. What is that? Okay, so very, very dangerous. So ApacheSpark. So ApacheSpark is a service in Bluemix as well. So you have the engine and you have the corresponding user interface. And in case of IBM, we are using Jupyter. Have you heard about Jupyter? So these are Python-based notebook-style web applications which can run all sorts of interactive source code like R, Scala, and Python, and many more. So we are using that heavily. So let me just show it to you. Yeah, by the way, that's the Coursera course which I'm currently developing. So it's like a preview. Of course, it has to oh no, it doesn't have to re-authenticate. So let's start with a very simple one. So who of you are Java programmers? Ah, they are dying out now. In Europe also. Okay. Python? More Python than Java. Oh, can we repeat that since we are not having that boom boom shake shake thing? Let's do it again. Who are Java programmers? 1, 2, 3, only a couple. Who are the Python guys here? Who are the JavaScript guys? Oh my god. What else? Scala? Scala. More Scala than Java. Yay. India is great. Never have seen that before. Anything else? Swift, Objective-C, C#. Okay, so that's nice. So that means you are well prepared for Spark because everything is about I forgot R. Any R programmers? 1. Okay. So this is Python. If we do that in Scala, it won't look very different. So I'm not typing this live because I'm getting old and lazy, but actually in my Coursera course, which will be published in 2 or 3 weeks, I'm typing all that stuff live. Actually all that what you see, I've been typing live and recording live. So, but what it does is, the central entrance point of ApacheSpark is the so-called Spark context, which gives you access to the cluster, okay? But in order to that this makes sense to you, I will show you only 1 or 2 little slide decks. So because we had this question initially, so that's not the correct one. So the internal name for this course is Analytics 0, because it's so basic that analytics didn't deserve number 1. But please open. Okay, so let's start with P1. Okay, I just walk you through briefly because we had this question initially. Okay, so the storage options, because we always talked about Cloud and NoSQL, but as you have seen, I could also use a normal SQL database, and if you have only a couple of megabytes of data, that's a very valid case because everybody knows SQL. If you have changing schemas, it becomes a bit harder because every sensor has some sort of other schema, and if you mix that all in one table, it becomes really weird. So in NoSQL, that's far more easy. And one thing which people don't mention normally is object storage. That's in our case based on OpenStack Swift, and it's the far cheapest option in storing something in the cloud. It's 4 cents per GB per month. You cannot compete with object storage at all. And the cool thing is, if you are using ApacheSpark, at the end of the day, it doesn't really matter what storage engine is in the background. You can use Spark SQL, you can write very complex SQL statements, but it gets translated in either calls to object storage or to MongoDB or CouchDB or to any SQL engine. So you shouldn't worry about storage too much, and you can also mix and match. But here's a little table which gives you a little idea. So the storage cost in SQL is high, as already mentioned, and also the scalability is very low. If you want to have double the performance and you put double number of nodes, you won't get double the performance, which is the case in most NoSQL databases and also in object storage. If you search a single item in 1 petabyte of data, then object storage is slow because you have to do something like a full table scan. You have to search through all the data unless you somehow create some sort of index. Okay, that's all about storage. Then, as promised, I just walk you through briefly. Yeah, let's skip the storage cost calculator. You will clearly see that object storage is the cheapest one. So let's go to the next one. So that's a bit more interesting. Who of you in this room knows what Hadoop is and how Hadoop works? Still nearly half. So for the other half, I just walk you through briefly. So it's about parallelization. If you have some workload to do and you run that in Java, you run it in a single JVM process, and if you want to run it on multiple cores, it's already a pain, unless you're using Scala or unless you're using the new Lambda functions in Java. But to parallelize this on multiple nodes, it's harder. So what you want to do is you have some sort of management JVM, which is called driver in Spark, and then you have executor JVMs, and you have multiple executor JVMs per node based on a number of cores, and also multiple nodes with multiple executor JVMs. In recent days, we had something on the bottom which was called HDFS. I will come to that later. But what we see currently is that the workload you are running is so much more CPU intensive now that basically any bottleneck at the storage level are not present anymore. Therefore, in the cloud service, which I will show later, we are not using HDFS at all. We are using Swift, OpenStack Swift, because it's the cheapest option and it is sufficiently fast enough. If it is not fast enough, if you really need I/O bandwidth, then you have to distribute your data across the nodes and basically partition your data to all the hard drives on all the nodes and create a virtual file on top of that partitions, and that's basically what HDFS does. But also, now we come to ApacheSpark. Who of you knows ApacheSpark? Okay, then I can go home. So then I think I can really quickly go over this. The central data structure in Spark is the RDD, the resilient distributed data set, which basically can distribute data on the main memory, of the aggregated main memory of all the cluster members. RDDs can be created from various sources, from HDFS. If they are created from HDFS, then the data doesn't get copied into the main memory at all. It just will reside on the hard drives distributed, and only in a lazy fashion will get read. In the case of object storage, it's similar, but if you, for example, read a file from a local drive, all the data will be copied into the main memory, which normally isn't a problem because of two reasons. You have a lot of main memory in such a cluster because main memory is becoming cheap, and if it doesn't fit into the main memory, it will get spilled to disk anyways. So it's like a big virtual piece of single memory where you can mess around with. Yeah, and the basic idea is you have to program a bit weird. You have to implement parallel programs, but once you do that, it doesn't really matter whether you are running on 1 KB or 1 petabyte. So that's the first class citizen, the RDD. Let me close a couple of windows, otherwise. So that's where I wanted to continue, basically. Number 4. Just for sake of completeness, about the programming languages. So I wanted to do the course in Scala, but then finally I've been forced into Python, but I'm now quite okay with that. Now I write a book about Spark in Scala, so I can do my Scala things. Yeah, so R is quite nice. For those who have ever worked with R, it's like a dream. If you have worked with R and you come back to anything else, even if it is Python, Pandas, NumPy, scikit-learn, you will hate it. R is so amazing. The only thing is you can't use it. It just crashes all the time. It's so slow, and once you process more than, let's say, 100 megabytes of data, it just is not usable anymore. That's the thing with R. You start to love it, and once you want to use it, it's not feasible anymore. That's my experience. So you have to stick with something else, and I think Python and Spark is not so a bad option, since everybody knows how to implement it. So everybody can more or less write proper Python code, but not every guy on the street can write proper Scala code. You can really scare people with Scala. So Python is not a bad option to start with all that stuff, which we will do. So only 2 slide decks left. This is this one. So who of you knows what a lambda function is? Okay. Who of you has used one in either Scala, Python, or Java, or R? It's even possible in R. Okay, good. Not too many. So a lambda function is basically the idea to create some sort of anonymous inner function, so you don't give the function a name. And Lisp was the first implementation, to my knowledge. Haskell was the most popular or most famous because it was mandatory at universities. Scala is the most recent representative, but Python, R, and Java also supported some sort of, so that's an arguable thing. But the idea is you have some sort of a function creator, and then you have an object. Your function becomes an object, and that object is serializable and can be sent over the network. That's the key thing in ApacheSpark. And the data is distributed on multiple nodes, and over the network the function is sent to the data and applied to the data, which is called apply in many programming languages. And what this basically does is, so you can see, apply is a function, and this function takes as first parameter a function. Like in C, a function pointer, but it's not so weird, it's just working. And the result of that call is that each element gets incremented by 1 because the function has been applied. Okay? So why are we doing that? Parallelization. Once we are implementing it this way, we can send the function to multiple distributed nodes. So let's have, for example, 3 nodes. We send the function to 3 of those nodes and apply the function in parallel 3 times. Without changing our code, you note? We don't change our function. We get the same result, we merge the result. And we even don't merge the result because it's resulting in an RDD, and the RDD is something, a way to aggregate data in a distributed fashion. So the RDD is a virtual list, and we can just keep the data on the machine where it has been produced and create a virtual RDD on top of it, and we are done. This is, by the way, something ApacheSpark does. And there is, I think, where we should start with the first video, the first demo. It's not a video, I have to. So SC basically is called a Spark context. That's your connector into the Spark engine from a plain Python or Scala or R or whatever supported language. And you tell the Spark context, please parallelize this collection. That means I have here a call to range 100, which generates a list from 0 to 99. And the result is an RDD. And as you can see, it's really, really fast because it doesn't do anything. It's completely lazy. You have just created pointers now. Only once you call count, so it's more about initialization and tier up and tier down, but it will take some time, and then it will tell you the number of elements. And I will start this other one in parallel as well. That's basically the way to take the first 10 elements. Imagine now you have an RDD with 1 petabyte of data. There is a function called collect, which copies all the data back to your single node. So I really discourage this because you will crash. If you have 1 petabyte of data, don't call collect. Okay? If you want to have a look at your data and you don't want to take the first 10, you want to have a good idea of the whole contents of your data, take the sample function and tell the sample function, give me 1% or 0.1% of my data. Okay? It's a RDD function. Okay, so let's implement one lambda function. Let's implement this easy one. I hope this mic doesn't fall on the ground. So we say RDD map. Map basically is a function which takes as parameter a function and applies the function to each element. In order to create an anonymous inner function, we say lambda. That's the way to do it in Python. X. So x is the input parameter of the function. And then we say x plus 1. It's exactly the same thing I was doing. And the result of the map function is also an RDD. So you are applying a function on an RDD and the result is an RDD. So you can easily nest and stack all that calls. And if we run this, so what do you think is the result? So the containing RDD is this one. What do we get if we run it? Any ideas? Yeah, okay, good. There's another interesting thing which we can do. We can also call collect. So there are more than 30 or 40 functions on the RDD, especially for aggregation and joining. You can do fuzzy joins using the Cartesian product, but that's all in the course. So you can, for example, say filter, and the filter function expects a function as parameter which returns Boolean. And if it's true, the value passes through. If not, it's filtered. So what's the result of this? It's a bit more complicated now. What? 1 to 9, yeah. Okay. So we can play this game immediately, indifferently, but let's stick with that. So once I've teased everybody with the RDD API, I basically tell everybody just forget about RDDs because you might know SQL, and I don't want the free update now. So we have RDD, so the RDD stays the primary first class citizen in ApacheSpark, but then we can wrap it with a so-called data frame. Data frame are very well known in R, that's the first class citizen in R, and also in Python if you're using the pandas machine learning library. And now we have data frames in Spark as well, and the very cool thing is those data frames, they are parallel. So no matter if you store 1 KB or 1 petabyte, you can use the same code and run it on the same engine. So there's an API which is really weird, and there's even a more weird API if you are using it in Scala, because the guys have created a DSL for this API. So we are not using that today because we are lazy, we don't want to learn anything new, we just use the SQL. The cool thing is, it doesn't matter whether you use the API or you use SQL, the execution will be the same, okay? Because the API calls and the SQL statements are translated in the same execution, in the same logical execution plan. There's another thing which is called dataset, which is only available for Scala and Java because the dataset API is strongly typed, and that's not possible in Python and not possible in R, so we are out there, so we won't cover dataset. But dataset was the idea in ApacheSpark 2.0 to unify RDD and data frame APIs. And I think they did make it. So schemas, so RDDs are schemaless, or schema on read, or schema in your head. And if it breaks, then the schema in your head was not the same like the data. Data frames have a schema. It can be lazy and inferred, or it can be explicitly defined. That's your choice. If you have time, I'll show you an example where you can read data from a cloud database. The schema then is lazy and inferred from the underlying schema of the source data. So one cool thing is in ApacheSpark 2.0 is the catalyst, which is optimizer. So you don't have to care about anymore, for example, if you join two RDDs together, about the size. So first of all, whether you use the API or SQL, ApacheSpark creates a logical execution plan. Then he rewrites it and optimizes it a bit, and he creates many physical execution plans. And based on statistics and on cost-based statistics, to be honest, Spark 2.0 has only one single cost matrix so far, but they are catching up. Based on the cost-based statistics, they choose the best physical execution plan, and it's this very same thing you have in relational databases now. But on distributed data stores up to 1 petabyte, 10 petabyte, and all open source. Okay. It all makes use of Project Tungsten, which has been introduced in 1.5 or 1.6. So the JVM is a very sophisticated piece of software, I have to say, even if Java programmers are dying out. But it's a general purpose engine, so it's not really meant for data processing. And most of the times the JVM is creating objects and destroying objects. That's why Java is so slow. And the other reason why Java is so slow is that it uses 48 bytes for 4-byte string. And then the GC, the garbage collector, calculated statistics, and it runs, and your JVM hangs, and all that stuff. And then the Spark guy said, okay, let's do this better than the garbage collector, because we know the life cycle of our data structures, and we basically decide when to create and when to destroy the data. So they are doing it like in C, free and malloc functions, basically. The data structures are very cache friendly, so the strides of access patterns are meant to not pollute caches, to read that data in sequences where it can make use of the caches, and it creates source code to avoid all that auto-boxing which Java introduced in version 1.5, which is nice for the programmer but bad for the JVM. And there's another thing which is called polymorphic function dispatching, which basically means during runtime the JVM finds out which function to call based on the signature of your function, which is also a waste of time. So that's all removed in Tungsten. And that's about Spark SQL, and I will just show you how to use it. Or do you already know that? Who knows how to use Spark SQL? 1, 2, 3, 4, okay. You're all stuck with the RDDs. So let's open a little demo for Spark SQL. It's not perfect, I have to say. It's not as cool as R, but they are doing not bad. So let's open this notebook. Where is it? It's, for example, this one. Why not this one? So this includes also the connection to Cloudend. And who is at IoT Next tomorrow? Nobody? You? Me too. And today night I will actually prepare the demo for it. It will be based on this notebook and your data, your test data generator. So something has changed here. In Spark 2.0 we don't have we have the Spark context, but it's only for back compatibility reasons. So the new friend is called Spark Session. But you can create a Spark session out of Spark context, fortunately. And you see I'm working really hard on that stuff, no? It's 200 times I've executed that stuff. So this is basically calling or using a connector. So you can implement connectors to backends, and that's connectors some IBM guys have written and open sourced for accessing Apache CouchDB and also IBM Cloudend, which is based on Apache CouchDB. So you specify basically the connector, you specify hostname, username, password, and database. So this is, for those who know MongoDB, that's something like a collection. Is it called collection? MongoDB? I think so, yeah. So in Cloudend and CouchDB it's called database, for whatever reason. So you need these 4 parameters, and the result of this call is not an RDD, it's a data frame, which has also a count function. But now it comes the really cool part. You can register this data frame as a temporary table inside the Spark SQL subsystem and execute ANSI 2005 compliant SQL queries against it. That's really cool, because the SQL queries, they get optimized and you get some sort of a local optima for your execution. It's definitely faster than the code you are writing if you are new to Spark, definitely. So the count is still running, because I think the first call is always, it's still loading data from, there's one thing which is interesting to note. The connectors, they can be implemented smart or not smart, and this one is still not smart, which means if you read the data, it basically copies all the data to an RDD, because data frames are also backed by an RDD. The RDD now lives in the main memory of this cluster, which is not a problem, but the smarter way would be to implement the connector in a lazy fashion. So once the data frame is created, it only returns a pointer, and only if you execute code on the data frame, then the data is read. And if you are even more smart, then selection criteria are passed down to the engine, which is, for example, the case if you connect Apache Spark SQL to Apache Hive, then the selections are pushed down to the Hive engine and also to relational databases. If you connect Apache Spark via JDBC to a relational database, the same thing happens. So now this was running, and I will just re-execute this one. Now you see it's faster. It's a select star from washing flat. And I think I will later on port the shake my device demo to this, because I need only 5 to 10 minutes. So now it comes to the point where it's still not perfect, because if you want to create an array, sometimes you have to create a local array for whatever reason. You have to create a SQL statement. That's still okay. The result is a data frame. The data frame contains row wrappers, so all the rows are wrapped in a row wrapper object, which you have to unwrap using still the underlying RDD, which is not perfect. I have written a complaint and got some comments, but yeah, it's open source. I would have to change it myself. So what you have to do in order to use the data locally, for example, to plot it, I think in module 4 we are talking about plotting in this course. Of course, we cannot plot with a Python plotting library and pass 1 petabyte of data to it. Therefore, we have to sample it, and here we just sample 10% of the data. And once we have sampled, we can call collect, and what we get back is an array containing the data. And what we then do is we use matplotlib of Python and create a box plot. Who knows what a box plot is? Okay, 2, 3. Box plot is a very, very cool thing, because it tells you about some interesting properties, and that's also the point where I stop this demo and hand over to myself, telling you about something about deep learning. But I will just tell you something about the box plot, because this is, for example, now hypothetical data from a washing machine about the voltage. I think in India you have 220 as well, no? Yeah, so 230, okay. Sometimes you have 0. We also know it's not a problem. So you see that in the box plot you see the mean immediately, which is 230. You see, I have to look this up, but that's most likely the variance. So most of the values are lying in here, and that's most likely the first quantile, which means 75% of the data lies in this interval, and those crosses here are the outliers. And with only, let's forget about the import, with only 2 lines of code you have drawn so many conclusions about the data set. If you use this on a petabyte of data, your box plot function will explode, but you can sample it down. And if you take a random sample of your data, you more or less will get the same distribution and the same insights of your data. Okay? So let's, I give you 2-3 minutes for questions, and then we dive into the deep learning stuff. Yeah? That's the reason why people are like Spark now, because they are exactly doing this. They use their R stuff, so they are accessing the big data using the hardware which they are already know how to write. Then they sample it down, and then they use the stuff they are already doing. You cannot plot big data because your plotting engine is good. You have already sampled it. Aggregated. There is, to my knowledge, in the ML, machine learning library of ApacheSpark, there is a histogram function which automatically calculates histogram data and I don't know, it's not that plot. It's the data which you use to plot.
Normalize
really good. With those frequencies you can deploy this. But if you have to send aggregate it out.
Yeah, I just had one question when you spoke about the obvious storage. Basically, when you go for searching, the cost will be very low. So, is it something apparent to partner database or something how we capture
ApacheSpark is basically behaving like a very big thumb size. So if you want to have some sort of index, you have to have this outside of the object store and other systems. For example, you can have the index on NoSQL database and actual data on the files in the object storage. You can work on either. You can even in ApacheSpark and ApacheSpark SQL, you can join data from SQL, NoSQL, and object storage in one single line.
I just have come across the Apache thing on a conceptual basis, and the one striking factor what I've read through is basically they say that Flink is more stream processing compared to Spark, where Spark is more it works in the micro batches. Still there is a very less latency when you compare the processing of Spark. Just share some on that.
So Apache Flink is Flink. You know what the word Flink means? It's German, because the Flink guys are German. It's the first top-level Apache project outside US. It's fast. Flink is German for fast. Especially the logo is that little squirrel, and if a squirrel runs fast, we say that squirrel is Flink. So that's the reason why it's called Flink. And the reason it's really Flink because I don't know if you have ever tried to process, for example, a stream from a webcam with ApacheSpark. Have you tried that? I have tried it and it's not smooth. There's always latency and you have always to wait. That's because of micro-batching. If you can live with that, you can go for ApacheSpark. If you can't live with that, then you have to go for streaming engine. And Flink basically is a streaming engine. So the internal architecture is completely different to ApacheSpark. The APIs on top, they somehow look similar, but the architecture is different.
They provide both the flavors that we have. They can work as a Spark as well. They can do the batch processing as well as streaming processing.
Both can do both, and but Flink is a streaming engine by nature. Yeah. And that's an idea which Google recently came up with, and they have created this incubator on Apache, which is called Apache Blink. And Apache Blink is basically data execution description language somehow, and it can run on top of Flink and it can run on top of Spark. And the guy said it runs better on Flink than on Spark. And they are very smart because it runs also Google Dataflow. So that's basic idea of Google. No? They open source TensorFlow and everybody is using TensorFlow, and if you want to speed it up, you run it on the TPU accelerators in the Google Cloud. And it's the same with the Apache Flink. But anyways, there's need for some unique processing, because what you do otherwise is the Lambda architecture. That means you have the same logic on a streaming engine and on a batch engine, and you run it in parallel. So you have semi-stable, semi-correct intermediate results, and in nightly batches you have the whole truth. That's the Lambda architecture. And Google states with Apache Blink and that Dataflow API sort of thing, you can run it on either Spark or Flink without using the Lambda architecture and get both. So there is a talk on Software Engineer Radio. That's why I know that so well, because I heard that while I'm in the gym. I always listen to softwareengineeringradio.org.net, and I really recommend that there's an interview with the Apache Blink developers. Okay, shall we try again this shake thing for 1 minute? I'm really curious whether this database is coming back or not. No, okay, go home. I will port this to ApacheSpark SQL, and next time it will run on ApacheSpark. So let's go very briefly to my deep learning demo, and then I think we are already over time. I let you drive home. It will take some time for you, or for those who want to stay for chat, feel free. I'm still here. All the IBM guys and colleagues are here later if you like to talk to them. So it's this one. Actually, those two guys are currently implementing a better version of this test data generator, which I'm using here. So what I'm using here is, let's go back to my presentation, that you know actually what I'm trying to show. So, blah blah blah. I want to talk to you about the brain of IoT and so on. I'll skip all over this. I will also skip the introduction to neural networks. Or who of you doesn't know how artificial neural network works? Still some. Okay, I will just briefly introduce it. The basic idea is that you have neurons. They are calculating some sort of mathematical function. You have input neurons which are directly getting data from your input table. For example, you have a table with 3 columns. You have 3 input neurons. You have a hidden layer. I will later come back to that, what that is good for. And then you have output neurons, and that, for example, could be used for binary classification. Okay, and the topology of one single neuron basically is doing nothing else than taking all the input from the upstream neurons, using a weight and summing them up, and then applying a nonlinear transfer function. That's basically the idea of neural networks. By using a nonlinear transfer function, the whole neural network can learn a nonlinear mathematical function, and that's basically the idea. And if you add multiple hidden layers, what happens then is that automatically the neural network will learn abstractions of your data. I will explain that later because I will use that in my demo. One example are convolutional neural networks. They are learning abstractions of that what the neural network is seeing. So if you train a neural network, a convolutional neural network with multiple hidden layers, the first layer will learn only ordinary shapes. And by the way, your brain is doing exactly the same. You have the same stacked topology in your brain, and your first thing, if you are looking at my hand, your first layer is only seeing lines and circles, nothing else. Okay? And the deeper you go, the more concrete the activations are. Activations means when are neurons firing, and they are firing basically if they see such things. Okay, and at the deeper levels they recognize faces. So they are actually the neurons which are firing are at the positions where a face actually resembles into such things what you are seeing here. Okay, I skipped that. You can basically train a neural network to learn the art style of an artist, but that's the statement I already said. You can learn a function with a neural network, with a feed-forward neural network, but you cannot recognize state. It has no memory. So the first idea was to insert feedback loops, and that makes it feasible for sequence learning, and in IoT we have sequences, so that might be a good idea. But there's a better version of it. It's the LSTM, the long short-term memory network, which includes a memory cell in each neuron, and this can do really amazing things, like learning the way Shakespeare wrote literature. So that's a text generated by a neural network. That's text generated by a neural network as well, mathematical publication. That's text generated by a neural network as well, Linux kernel C source code. And it outperforms all the traditional algorithms in anomaly detection. That makes it interesting for IoT. So that's figure from that publication. You see the green lines, that's normal behavior. You see the blue lines, that's anomal behavior. The normal behavior, the sequence or the temporal sequence of normal behavior is learned by the neural network, and the neural network can decide when it sees data which it hasn't seen before. When it sees a sequence which it hasn't seen before, it drops. So the probability that this data is something which it has seen before is dropping to nearly 0, as you can see here on the top left chart. Another thing is what you can do with such types of neural networks is forecasting. So The state of the art is kernelized regression. That's a method in machine learning, which has a 8.3% error on that data set. You can use a frequency neural network. I will come back to that in my demo, what a frequency neural network is. You get down to 6.7. You can use a deep feed forward network, 5.9, and you can use a network with state. You are up to 0.8%. Yes, question?
How is DeepLearning time series different from regular regression models? How is it going to differentiate itself? What kind of errors are avoided? Can you help quantify errors?
I'm not a super expert in that traditional way of doing it, but what you, for example, have is the ARIMA model. That's the model which basically calculates a moving average. And even if you are completely stupid, you can see that by calculating a moving average, you never ever can get any recognition of some complex sequence. And that's basically my statement. And I haven't seen any model so far which is capable of learning complex sequences. The only thing what you can do is you can decompose the sequences, and you can recompose the sequences with your decomposed parts, and then you can calculate the recomposition error. It's the most sophisticated traditional machine learning algorithm which I've seen so far, but it is outperformed by those. And you have to look at LSTM networks for time series, especially. Yeah? That's only a recurrent. That's not even a LSTM, and it gives you 2.8%. And you can see the blue and the red line. They are really nearly the same. Okay. So that's the key statement for today evening. Then you can forget everything else. LSTM is Turing complete. So LSTM can basically, if you have enough data, learn anything a normal ordinary programmer could implement in an algorithm. Okay, you shouldn't forget about Node-RED and all that stuff. Sorry for that. Problems with neural networks, then I really will dive into the demo, is they are very, very expensive to train and to score. But we are catching up. So 2009, cluster of 16,000 cores is now inside a GPU card, a Titan, NVIDIA Titan, which we basically are renting in our cloud for $1 per hour. So you have now for $1 per hour a 16,000 core equivalent of 2009. And if you use specialized hardware, an ASIC, application-specific integrated circuit, like IBM True North, you have the same computing power, and this consumes only 4 watts. Okay. And last slide on this, we are currently building such a cluster with such a chip with 4 billion neurons and 1 trillion synapses. And in contrast, the human brain has 100 billion neurons and 100 trillion synapses, so it's around 4% of the human brain. Of course, the human brain works differently, very, very different, but yeah, just to give you an idea. So that's basically the architecture which we are using for real time, and now let's do the demo. So the demo is based on the idea for a predictive maintenance and quality use case. You have bearings in a manufacturing plant which are breaking, and you want to prevent them to break because you want to detect failures or potential failures. So what you can do is you can attach 50-cent vibration sensor on it, which you have in your smartphone, but you don't have a vibration sensor on your, no. The Raspberry, no, you have to have the SenseT or the Groove Pi. I think then you have a accelerometer as well on the Raspberry, but it's I think it's a 50 cents device. What it does, it sends you the energy of the vibration in each axis, and I've written a simulator for that, and those two guys have made it perfect, and it generates vibration data based on a physical model which is called the Lorentz attractor model, which is known by the that's basically the simulator. You can deploy it, and like the Node-RED stuff from these guys, and then you have the simulator up in the cloud, but wait for 1 or 2 days, then you have the new version of it, which is far better. But it basically creates data like this, and that's a so-called phase diagram. That's a way to visualize time series data on multiple dimensions at the same time. So the line is the timeline, and the line reflects basically the change of the three values. So that's some sort of vibration pattern, and you see that the vibration pattern oscillates between two semi-stable states on the left and the right side. And now you can tell the simulator this is a broken device and generate the data accordingly to that. Then the data looks a bit different. Most of the people are not familiar with phase diagrams, so we still give you the ordinary run charts. So that's a chart where you see that on two axes the vibration pattern is oscillating between two states. You can clearly see that. And also for the broken state you can't see that anymore, but you see that there's much more energy. So any idea how I can write a classifier using deep learning or using some traditional algorithms on such type of data? Very easy. What transformation do I have to do on the time series in order to write a very easy classifier using support vector machines? Any ideas? On the publication there was a title called Frequency Neural Network. So frequency. So I do fast Fourier transformation and get the spectrum of the vibration for the healthy and for the broken state. And that's something I can train an ordinary machine learning algorithm, but I can also say, okay, I don't care about the energy levels and the distribution of the frequencies. I just let a normal ordinary feed-forward network being trained on that. But I want to create an anomaly detector. So what I do use here is an autoencoder, and that's the last neural network which I will show you today, I promise. But that's also the most, very, very most interesting one in my opinion, especially for IoT, because what you do is here, that's the feed-forward network, and on the left and on the right hand side you show the network the very same data. So the network has to learn to project the same input data to the same output. But there's a catch, there's only a 2 neuron wide middle hidden layer. So that is called a bottleneck. And that basically removes all noise and all redundant data and gives you a low dimensional representation of your data. And that's what basically autoencoder does. So that autoencoder will learn how normal data looks like, and will represent that in a very low dimensional vector. And after that, if it sees new data coming which it hasn't seen before, then reconstruction is a bit harder for that neural network, and that we will see, okay? So let's run this, and then I leave you. So I'm using in this case lasagne, which uses Theano. So lasagne, who knows lasagne? The food? Yeah. Dish, okay. That's basically the idea, because the neural network has multiple layers, and when you are cooking lasagna you can simply put multiple layers, and that's the basic idea. If you want to put multiple layers using Theano or TensorFlow, it's a pain in the ass. It's really hard. It's like you have to be a mathematician to do that. If you use lasagna you can just add layers. I will show you later how that works. So let's basically run this. I'm using some plotting function. I'm still using HTTP, so those guys have modified the test data generator that it runs MQTT. So again, I plot all the data like you have seen in presentation. It's still running. So star means it's running. And once you see a number here, then that's the job ID of the ApacheSpark job, basically. Yeah. We're almost done. So I'm doing a lot of messing around with RDDs and copying data and creating arrays to plot. Like I said, you cannot plot a petabyte of data, so that's the stuff I'm doing now. Here, still waiting. So it's not normal that it takes so long. So let's continue and let's see whether it stops. I have to run this as well. And fortunately, we see the output of the previous run. So that's basically the point where you train the network. Now first I tell you how you create a network. So that's where Lasagne kicks in. So you say input layer, 3000 neurons, hidden layer, 2 neurons, output layer, 3000 neurons. If you do that in TensorFlow or in Theano, it's like 20 lines of code. I think there's also a library for TensorFlow called thlearn. Or if you want to get really parallel, you can use DeepLearning for J on ApacheSpark, which basically does the same, but then it's really in parallel. So is this finishing? No, okay, not finishing. No worries. What you would have seen is if it would have run is the output of that loop. So what you can do is you basically can train the neural network. So you can see here that's training the autoencoder. You have seen that I was creating it by defining a topology of 3000 neurons for the input, 2 neurons for the hidden layer, and 3000 for the output. And here I train the autoencoder with itself. So I have train and as input and train as output. And if you continue to train, then the neural network will learn how the data looks like, and the reconstruction error goes down because the neural network will adjust to the data which it has seen. Then you have only after 10 iterations reconstruction error of 0.9 instead of 1.0. Now let's switch the test data generator to the broken state, do it again. You get a reconstruction error of over 1, and let's do it and switch back, and then you get 0.9. So that's 0.9. That's the basic idea. I would be happy if I could have shown it to you live, but it somehow not working. But yeah, but basically that's the way how to implement an anomaly detector. And I have to show you one slide. Sorry, one very last slide on that particular publication. So which one do you think I have implemented of those 4? What? It's me? Yeah, exactly. So I've done FFT, fast Fourier transformation, and applied the spectrum to the neural network. And what I've told you, if you have a deep nested structure, the neural network can learn the feature transformation on its own. And that's exactly what happened here. If you have a deep feed-forward network without the frequency transformation, you are outperforming the FFT. That's cool, no? And if you add memory to it, you are outperforming all the rest. Okay? Good, I'm done. So any questions? Good. Okay, so for those who want to stay, I'm still here, half an hour more or even longer, and the others, I wish you a lucky journey home to your family or whatever. Thank you for coming.
Thank you very much.